Okay, now, of course, we are presenting some important concepts concerning a new chapter, inputs and production functions. Of course, here we're going to be talking about, how inputs are used, are used in order to produce finished goods and services. Remember, consider the following important concepts here. Production of goods and services consists of transforming, inputs such as labor, power, raw materials, and the services provided by machines into finished goods. Example, semiconductor producers, So when we're talking about, production of goods and services, there exists certain process. You have inputs in one side, okay, and you have outputs in the other sides. So the firm will use the inputs, through a certain technique, production function, and then at the end we have finished goods. An example of this, of course, semiconductor producers. Semiconductor producers is a major firm that specializes in the production of, chips. Now, as you know, semiconductor producers uses the labor services provided by its employees, along with capital services provided by, robots and other, processing equipment. Of course, with some other, resources, such as, silicon, in order to produce, chips. So here we're talking about, the importance of using these inputs in order to, produce output, such as chips. Now, when we're talking about inputs, remember, we have inputs, or, another name for inputs is factors of productions or resources. We have, of course, as you know, 4 kinds of inputs or resources or factors of productions, such as labor, which consists of the physical as well as the mental, services, that are used to organize the other, inputs to produce goods and services. Of course, you have the land, which consists of the natural resources, and we have many natural resources that are used, to produce goods and services. Of course, we have capital, which actually consists of finished produced goods. These produced goods, such as machines and equipment, they are used to produce other goods and services. Okay, and also we have entrepreneurships, which actually consists of the innovative, ideas or talents that are used to combine the other resources in order to produce goods and services. So the productive resources, such as labor and capital, equipment that the firm uses to make goods and services, are called inputs or factors of production. We have already discussed that. Of course, the amount of goods and services produced is the firm's output. So you have in one side inputs, okay? The firm will use these inputs in order to, produce the goods and services, the output in the other side, okay? So you have output, okay, and you have inputs. Remember that real firms, such as the semiconductor firm, can often choose one of several combinations of inputs to produce, of course, a certain volume of outputs. For instance, semiconductor firms, real firms, usually they have in their banks many inputs. For instance, here, if that semiconductor firm wants to produce a given number of chips, they can do that using, of course, workers and no robots. Or they can use a few workers with, with more and many robots. So a firm, a real firm, such as the semiconductor firm, of course, can choose from among many of its inputs in order to produce the finished goods, okay, and services. Okay, they either can use many workers with no robots, or they can use a few workers with many robots. Now, therefore, the production function basically tells us the maximum quantity of output the firm can produce given the quantities of inputs that it employs. Okay? Now, the production function, we can state it like this. If the production function, if the firm is using two inputs, such as labor and capital, then we say we can write the production function formula as this. Q is a function of labor and capital, where Q is the amount of output. Okay? And then L refers to a labor and K refers to capital, which means that, the output is a function of the inputs. Okay, when the firm uses the inputs, it basically produces an output which refers to as Q. Okay, the production function may shift if there exists a technological progress. Remember that the production function, of course, is based on certain exogenous technological conditions, and these technological conditions over time may change, and the change of these technological conditions will give us a phenomena, and that phenomena is called a technological progress. Okay, and then when these these technological backgrounds or conditions change over time, then we expect the production function to shift. Okay, so the change in the technological conditions, the exogenous technological conditions, is known as a technological progress. Okay, and whenever they change, of course, we will have a shifting of the production function. Of course, this equation Q equal a function of K and L tells us the maximum input, tells us the maximum, of course, output the firm can get from a given combination of labor and capital. Okay? Yeah, in other words, as we studied in production possibility frontier, okay, the production possibility frontier usually give us the maximum output, okay, given the resources that are fully employed and a certain level of technology. Same thing here, the production function, this one here, of course, this equation will give us the maximum amount of output the firm can get from the combination of the labor and capital it uses. Consider the graph of a production function for a single input N. Okay, this is the graph. You know that sometimes mismanagement, okay, in the firm can cause the firm to produce less output. So consider this situation here, this exhibit or this graph. It shows a production function that is a function of one input, that's labor, along the horizontal axis, and of course output is along the vertical axis. Now, as you can see, points that are on the production function and below the production function, inside the production functions, or these constitute the production set, okay, which actually basically the feasible, the technically feasible combinations of inputs and output. Okay. Now, of course, we know that the production function was the maximum. However, as I said, sometimes inefficient management, can cause the firm to produce less. So points such as A and B below the the production function, of course, inside the production function set are technically, of course, inefficient. This means that the firm gets less output from its labor that it, that it could. So when the firm reduces at A and B, it means that it is in situation that is technically inefficient because it produces less output. Okay? How about points C and D, of course, along the boundary of the production function, of course, are technically efficient. Why? Because at C and D, the firm produces, of course, as much as it can, given the amount of labor it employs. Okay? Now, remember that the production function, whether it is that one, a function of labor and capital, or this one, which is the production function that is a function of one input labor. When we invert that one, okay, it's a Q is a function of L, okay, such as, for instance, Q equal, L squared, okay. However, when we invert this production function, okay, we're going to come up with another function, okay, which is L in terms of Q, and that function is called the labor requirement function, okay. So, and this function, the labor requirement function, when you invert the production function, okay, give us the maximum amount of labor required to produce a given amount of output Q. So an example of this, so you have a Q as a function of L. When we invert that function into L as a function of Q, we come up with something with another function that is called labor requirement function, which gives us the maximum amount of labor required to produce a given amount of output. So this example here shows you exactly what to do. Suppose here, given that Q equal L squared, this is the production function. Q as a function of L squared is a production function, then L equal radical Q. So when we invert this one here, okay, then we come up with L is equal radical Q. This is the labor requirement function, okay? Now, therefore, to produce an output of 25, if we want to produce an output of 25, then how many units of labor required? Of course, 25, we plug a 25 under the radical over here, and we come up with L equal 5 units of labor that are required to produce, an output of 25, okay? Of course here, then I'm just discussing what I'm saying over here. Therefore, to produce an output of 25, then the firm at least needs 5 units of labor, since the production function shows us the maximum attainable output from a given combination of resources. Therefore, we can sometimes write Q less than or equal FLK. Remember, because sometimes the firm will produce less because of inefficiency in the management. Then instead of writing the Q equal a function of L over K, if we are talking about we have two inputs that are used to produce Q, instead of saying Q equal function of L over K, okay, that shows the maximum level of output, we can write Q less than or equal the function of labor and K. This is used to emphasize the fact that the firm could, in theory, of course, produce an output that is less than the maximum attainable output. We showed that over here in the production function, which is a function of only one input, and we said that points A and B, are produced, but these are inefficient, points, because the firm produces less output. So in theory, the firm could produce less output, less than the maximum output. Okay. So in order to show this phenomena or this case, okay, that the firm might produce less than the maximum, then we write this over here to show that the firm could, in theory, produce less than the maximum output. To study the trade-offs, of course, facing real firms, of course, we have to consider production functions with more than one input. Okay, more than one input. So here we're gonna, of course, consider a production function with two inputs, namely labor and capital. Okay, so let's here see this table, okay? Consider this table that basically consists of capital units, capital, which is the input capital, and the labor. The labor is along the, this side, and capital is along the row side over here. And, the capital ranges from 0 all the way to 30 units, okay? Capital, of course, here is expressed in thousands per machine hours per day. It ranges from 0,000 machines per hour per day, 6,000 machines per day, 12,000 machines per day, and so on and so forth. Same thing, labor ranges from 0,000 machines man hours per day, all the way to 30,000, man hour per day. Now, the numbers inside this table represent output. Also, output also is in, of course, in thousands, of course, in thousands semiconductor chips per day. Okay, for instance, 5,000 semiconductor chips per day, 15,000 semiconductor chips per day, and so on and so forth. Now, of course, now if you look at this table over here, to understand, how output changes over here. Now, let's say if we fix, capital at any value over here. Let's say when fixing the capital, amount of capital at 18,000 machine, hours per day, okay, and let the amount of labor varies. Okay, we fix K at 18, and then let L varies from 0 all the way to 30. We notice that, when doing so, we notice that we pass through 3 regions, okay? We pass from increasing, marginal retains to labor, decreasing marginal retains to labor, and, of course, decreasing, total retains to labor. So let's look over here. Let's say when fixing K at 18, okay? Now, and L is allowed to vary from 0 to 6 all the way to 30. What do you notice over here? The amount of output increases, from 0 to 25 to 81. As you can see over here, when the amount of labor increases from 6 to 12, that is, the amount of labor increases by 100%. Look at the amount of output increases by over 200%, 224%. So the region from 0 all the way to 12, it represents the increasing, marginal retains to labor. What that means, it is the region, whose output increases, with the additional labor at increasing rate, at increasing rate. So this is the, the region that's called increasing marginal retains to labor. Now, which is actually from 0 to 12. Now, what about from 12 to 24? As you see that, here we can see initially the amount of output increases, as the labor increases, all the way up to 24. Beyond, L equal 24, the amount of output decreases, as you can see, becomes 127 rather than 162. Now, what about the region from 12 to 24? The region from 12 to 24, yes, it experiences that output increases, however, it increases at decreasing rate. Look over here, here, 69, from 81 to 137, the percentage increase in output is 69%, okay? What about from 137 to 162? It is 18%. It increases, the output increases, but it increases at a decreasing rate. So the region from 12 to 24 is called, decreasing marginal retains to labor, which represent the region whose output, increases with the additional unit of labor, but at a decreasing rate. This is the decreasing margin retains to labor. Now, beyond this, we have another region beyond 24,000, units of labor, man hours of labor. Beyond this, as you can see, we have a region that's called, decreasing total retains to labor. As you can see, the amount of output decreases. We've got 762, now we have 127. However, from 0 all the way to 162, the amount of output increases. However, after that, after L24, after L equal 24, the amount of output decreases. So now we have here the decreasing total, total retains to labor, which represents the region whose output decreases, with additional labor. Now, of course, we're going to use this one here later on to study, isoquants, to study the isoquants. Now let's look at the marginal product of an input. This is the definition of marginal product of an input. Marginal means additional. So the marginal product of an input is the rate at which output changes as the firm changes the quantity of one of its inputs, holding the quantities of all other inputs fixed. Now, if we are talking about an output that is a function of many inputs, and if you want to find the marginal product of one of these inputs, then of course it is, the rate at which output changes as the firm changes the quantity of that input, holding all other inputs fixed. So to make it easier, we're going to consider, of course, an output that is a function of two inputs, namely labor and capital. So, and we want to find the marginal product of labor and marginal product of capital. How are we going to do that? Look over here. Marginal product of labor, which is the change in the quantity of output, Q, over the change in the quantity of labor, given that K is fixed, holding K is fixed, and which is, of course, using the derivative over here, which is delta Q over delta L, holding K is fixed. I'm going to give an example to show you how to calculate the marginal product of an input. So the same thing, the marginal product of capital is equal to the change in the quantity of output over the change in the quantity of capital, because we're talking about the marginal product of capital, which is holding, of course, the other variable or the other input fixed. So if we're talking about the marginal product of capital, which is the change in total output in Q over the change in that input, which is K, holding the other input, which is L fixed. If we are talking about marginal product of labor, we are talking about the change in Q over the change in labor, holding the other input, which is capital fixed. And in an equation, it's going to be like this. Now, here we have an example. Consider the production function whose equation is given by Q equal radical KL. So it is a function of two inputs, namely capital and labor. Calculate MBL and MBK. So we're going to apply these formulas to calculate MBL and MBK. Notice MBL is gonna be equal delta Q over delta L. Of course, holding K is fixed, which is equal. The easiest way to calculate this one, to take away the radical first. So we say here, Q equal K L, Okay, we take away the radical, become K L 1/2, which is equal K 1/2 L 1/2. Okay, so we take away the radical term, and instead of that we use the numbers like this, the equation like this. Okay, now we want to find the derivative of Q, of course, the derivative of this with respect to L. Of course, K is going to be fixed, like a constant. Okay, so here, it's going to be K is fixed. If you are unable to understand that K is fixed, just use, use it as well. U times V. You remember? U times V. Okay? Now, we need to find the derivative. So here, MBL is going to be equal, the derivative of this one here, because K is fixed. K is fixed. So it's 0. U prime V plus UV prime, okay, plus U prime V plus UV prime. Okay, U prime V is 0 here, plus U V prime plus U times V prime times 1/2 and 1/2 minus 1, which is equal, of course, K 1/2 times 1/2, of course, L minus 1/2. Okay, becomes like this. So now I simplify this one more. So I come up with what? 1/2 K 1/2 over what? Over L 1/2. Of course, L minus 1/2, of course, becomes that in the denominator, and that becomes what? Becomes 1/2 K over L, 1/2, which is become 1/2, K over L. Okay, becomes like this, 1/2 K over L. Okay, we retain that to the original function, shape of the original function. The same thing can be, of course, said about, of course, MBK. So here, MBK is going to be equal, of course, delta Q over delta K holding L fixed. Okay, so we're going to have is equal the same thing as you can see, K 1/2 L 1/2. Okay, we're going to say U prime V plus UV prime, the product rule of the derivative, K, now we're talking about K now. So U prime, the derivative of this, okay, which is equal 1/2 K, of course, 1/2 minus 1, of course, U prime V. This is V over here. Okay, this is V. So now plus UV prime, of course, 0, plus 0, because U prime, okay, plus U prime V plus U V prime. The derivative of L is 0 because it's constant. Now, so what we get over here? We get, of course, 1/2 K minus 1/2. 1/2 minus 1 minus 1/2, of course, times L 1/2, which is equal 1/2, of course, L 1/2 over K 1/2, which is equal 1/2, you get L over K. Okay, L over K. And this is the answer for the marginal product of capital, and this is the answer for the marginal product of labor. Okay.